Welcome to 3D Time, from transportation to physics. My name is Ralph Gilman, and this is Part 3, Kinematics 1. What is kinematics? Well, kinematics is the study of motion. What is motion? And it describes, it doesn't explain motion. So we don't talk about forces. That's covered in dynamics, which is later. It talks about things like speed, velocity, and acceleration. So we're going to be looking for the corresponding terms in 3D time. What is motion? Well, we're going to begin with motion as a primitive concept that we understand in some way. So we're going to define space and time in terms of motion. We're going to do that by comparing motion to a reference motion. Space is an asynchronous comparison to a reference motion, such as comparing with a ruler. Time is a synchronous comparison to a reference motion, such as comparing with a clock. Now, space and time, space is observed asynchronously, such as with a picture or sculpture, and time is experienced synchronously, as with music or dance. Space has direction relative to a place, such as dancers converging at a place on the stage. Well, time also has direction relative to an event, such as dancers converging at a point in time. What is speed? Well, speed is a change of distance per unit time. So the average speed, we'll call v, is delta s, the change of distance, over delta t, the unit time. And instantaneous speed can also be defined as ds dt, and that's what's used in science. We'll talk about that later. Now, speed is a magnitude, so it's greater than or equal to 0. A negative speed doesn't make sense. The units for speed would be like meters per second, kilometers per hour, miles per hour. And it's important to note that the independent variable is time in this case, and the dependent variable is distance. So what if we switch that around and we said the independent variable was distance and the dependent variable time? Well, that's called pace. So pace is a change of time per unit distance. The average pace, we'll call u, is delta t, the change of time, over delta s, the unit distance. Similarly, an instantaneous pace can also be defined as u equals ds dt, or dt ds. And pace is a magnitude as well. It's greater than or equal to 0. So for example, in walking, running, or cycling, pace is often used as minutes per kilometer or minutes per mile. And the independent variable is distance. So for example, if you have a fixed track length for a race, then that's given. And what you're measuring, what the dependent variable is time. That's what you're focused on. One interesting thing is that lower numbers means a faster pace. So, because that means that the shorter amount of time is used. Let's compare speed and pace. Well, they're inverses. Pace is the inverse of speed, and speed is the inverse of pace. Now, that means, of course, that they cannot be 0, at least as far as comparing them goes. But in a sense, speed and pace are equivalent. If you have one, you can get the other. What if the speed is 0? Well, that means there's no motion, but the time continues to change. Now, what if you have a 0 pace? Well, again, there's no motion, but the distance changes? Well, this is because distance is independent, so it changes on its own. The track length is the track length. It's a difference, and it's independent of whether there's motion or not. One application of this is with pre-trip planning. Say you have an appointment, and so the destination is fixed. Well, that means that the independent variable is length. And then you want to focus on time, measuring time, and you want to get there on time. And you want to know what route takes the least amount of time, and you want to know what time to depart. Well, these are all time questions, and so they involve questions of pace and 3D time. Now let's consider circular motion in space and time. Look at a clock angle from noon to 3. Is that an angle in space or in time? Well, it's both. You've got both the angles and the circumference and the radius in space and in time. Look at the circle in space. There's a space angle theta, a circular arc s, and a radius r, such that theta equals the arc over the radius. But there's also a circle in time, the rotation angle phi, rotation time t, and a period radius q, such that phi equals t over q. Now consider orbits and rotations in space and in time. In space there is a circumference s and a radius r. And in time there's a period t and we'll see a period radius q. Now the circumference is also known as a wavelength. For the circle in space, we have the ratio of the circumference over the radius equals to 2 pi. So in other words, s equals 2 pi r. And in time we have a cycle, and we're going to define the period radius q as the ratio of the period t divided by 2 pi, so that t equals 2 pi q. Now we're ready for angular speed. We have the angular distance per unit time, v, which we'll look at as a frequency f or a time rate of rotation, omega, which is equal to 2 pi times the frequency. So the angular speed v is equal to a ratio of the circumference divided by the period, or a ratio of the radius divided by the period radius. Now, if s is 1, then the angular speed is equal to the frequency. Or if r is 1, then the angular speed is equal to the time rate of rotation. So that v equals sf, which also equals r omega. The units are meters per second, revolutions per minute, cycles per second, or hertz. And the independent variable here is time, so that the dependent variable is an angle in space. Angular pace. We have the period angle per unit length, which is the angular pace, u. We'll define a periodicity, h, and a space rate of rotation, psi, which equals to 2 pi h. Now the angular pace u is equal to a ratio of the period divided by the circumference, which also equals the ratio of the period radius divided by the radius. Now if the period is set equal to 1, then the angular pace is equal to the periodicity h. Or if the period radius q is equal to 1, then the angular pace is equal to psi, the space rate of rotation, so that u equals th and equals q psi. The units are seconds per meter or cycles per meter. And the independent variable here is length, so that the dependent variable is an angle in time. In conclusion, we began with motion and then defined space and time in terms of motion. We looked at a reference motion and asynchronous and synchronous motion. We defined speed and pace, as well as an angle in space and time, and then angular speed and angular pace. Continue now with Part 4, Kinematics 2.